In this problem, we have another non-homogeneous equation, which we will use method of undetermined coefficients in order to solve. We begin first by finding the corresponding homogeneous equation. Because the solutions of the homogeneous equation also solve the non-homogeneous equation. As we have previously done, we find the characteristic polynomial, which when we solve, we find that the eigenvalues are both imaginary, where in this case lambda is equal to 0 and mu is equal to 3. Using our guidelines for the fundamental solutions, we find that the fundamental solutions are going to be the following. Y1 will equal the cosine of 3t, and y2 will equal the sine of 3t. And you can verify that these are indeed linearly independent through the Wronskian determinant. And so in which case you'll find that the homogeneous solution to this equation is a linear combination of the cosine of 3t and the sine of 3t. Now looking at the particular solution, again we observe, as was the case in the last problem, that we have two functions from different classes that are creating the right-hand side of this equation. And so we can solve each individually and then superimpose the two particular solutions. I'm going to start first with y double prime plus 9y is equal to t e to the 3t. The guidelines suggest that the function that is going to satisfy this would be of the form yp is equal to at plus b times e to the 3t. We can find the first derivative of this, which will simply give us ae to the 3t plus at plus b e to the 3t times 3. And I strongly recommend in this case that you simplify as much as you possibly can. When we do, we will find that we get the following: 3at plus a plus b all times e to the 3t. This will make it easier for us when we have to go find the second derivative. And we would find when we do the second derivative, taking the derivative of the first function, we would end up with 3a e to the 3t plus 3at plus ab times e to the 3t times 3. Again, taking the strong guidance of simplifying so that we end up with 9at plus 6a plus 3b all times e to the 3t. We can then plug these into our equation, which in this case will give us the following: 9at plus 6a plus 3b all times e to the 3t plus 9 times our original solution, which is AT plus B e to the 3t, which must all add up to be TE to the 3t. If we go ahead and combine our like terms, you will find that we will end up with the following: 18AT plus 6A plus 12B, all times e to the 3t, and this must equal t times e to the 3t. As was the case previously, we will equate our coefficients so that whatever we see on the left has to equate to what's on the right. In our first situation, we find out that 18a has to equal 1, in which case a is equal to 1/18. We find out, secondly, that 6a plus 12b has to add up to be 0. Plugging in our value for a, we would end up with the following. And so we would find that b is equal to -1/36. And so these are our two coefficients that are going to go into my particular solution, which in this case is going to be given by 1/18 times t minus 1/36 all times e to the 3t. And that's the first of my particular solutions. Now, for the other particular solution, since it is just a constant, the guidelines specify that when I go to solve the following equation, y double prime plus 9y is equal to 6, I just simply guess that it will be a constant a, which, thank goodness, is much easier than dealing with the function that we just did. Plugging in what we know, we will find out that we get 0 plus 9a is equal to 6, whereby we find in this case that a is equal to 6/9, or 2/3. And so in which case, the particular solution we're looking at for this part of the problem is just simply 2/3. Now that we have our two particular solutions and the solution to the homogeneous equation, we can combine them, obtaining the following. Y is equal to C1 cosine of 3t plus C2 sine of 3t plus 1/18 t minus 1/36 e to the 3t plus 2/3.